Hi, in the previous video in the series of area formula, we justified the definition of Jacobian by looking at linear maps. In this video, we complete the next important phase of the proof of area formula, and that is justifying why there is a derivative in the first place to begin with. And that is due to the amazing result called Rademacher's theorem, which says that any Lipschitz map between Euclidean spaces is differentiable almost everywhere in the domain. And by differentiability here, we mean it in the strongest sense of the word, which is Frechet differentiability. That means if f is differentiable at x, then there exists some linear map between the same spaces such that f is approximated very closely by the linear map in the neighborhoods of x0. And this linear map L, if it exists, we call it the derivative of f at x, which is a linear map again, and we can identify, as we've been doing throughout, with the matrix that it is represented with. Okay, so let's see why Rademacher's theorem is so remarkable by looking even at the simplest case of maps that go from R1 into R1. So the first example, probably the simplest example of a Lipschitz map from R1 to R1 is that of the absolute value of x function. And that example, unfortunately, scares everyone off by that break it has at the origin. And so we decide that Lipschitz functions are not differentiable. They don't have a derivative. They can have breaks, no tangent, and the end of the story in undergrad. Unfortunately, what is not told is that this behavior at zero is not generic. No matter how crazy a Lipschitz function you can build, the set of points where you don't have a tangent, which means the points where you don't have a derivative, only makes up a measure zero set. And let's see. So what is f R1 to R1 Lipschitz? That means fy minus f of x divided by y minus x, if we take absolute values, is always bounded by some L for every x and y that are not equal. So L here is the Lipschitz constant of f. And this is all that Lipschitz, being Lipschitz, gives us. Rademacher claims that under this condition, then this limit, where you fix x and let y go to x, exists for almost every x. And that is why it's quite surprising. Just from the fact that the fractions are bounded, you deduce that the limits, the infinitesimal behavior, is controlled in the nicest way possible. The proof in 1D case, so for R1 into R1 Lipschitz maps, follows the following path. First, you observe that Lipschitz functions, the Lipschitz class, by definition, is contained in the absolutely continuous class. So a function is Lipschitz, then it is also absolutely continuous. Just by definition. So I refer to Wikipedia page as a great starting point for absolutely continuous functions and their definitions. But all I will need here is some properties of these functions. So if f is absolutely continuous, then it turns out that f is actually difference of two monotonically increasing functions. So g and h are increasing, not strictly increasing. They could be constant. And themselves absolutely continuous. Okay, so why does it make life easier? Because it's quite easier. Well, let's say standard, not easy. It uses some facts. That monotone functions are differentiable almost everywhere on their domain. Okay, so this then gives us the almost everywhere differentiability of the function f. You remove two null sets, one for g, one for h, and then f is differentiable everywhere else. So conclusion becomes that absolutely continuous functions are differentiable almost everywhere. So Lipschitz being absolutely continuous, that means then Lipschitz constants are differentiable almost everywhere. But there's actually more than that. So the derivative is nicer than that of just a merely differentiable function. So there are some functions that are differentiable almost everywhere, but their derivatives do not behave nicely. Let me give you an example. The counter set, not the counter set, counter function is an example of a continuous function that monotonically increases, and the derivative is actually, it exists and is equal to 0 almost everywhere on this interval 0, 1. F of 1 equals 1, f of 0 equals 0. So f of 1 minus f of 0, which is equal to 1, is not equal to the integral of derivative from 0 to 1. That means the fundamental theorem of calculus does not hold for this particular function. Fundamental theorem of calculus is never stated with the right assumptions in undergrad courses. So for some time, we may be under the impression that, well, whenever you have a derivative, you have this. That's not the case, as this example clearly shows. Absolutely continuous functions are characterized by the fact that the fundamental theorem of calculus holds for them. In other words, we can characterize them by this condition. So the precise statement is that if on compact subsets at least is absolutely continuous if and only if f prime exists almost everywhere, it is integrable, Lebesgue integrable, and integral from a to x of f prime of t dt in the Lebesgue sense is equal to f of x minus f of a for every x in a b. So that's a great characterization of absolutely continuous functions. So in particular, all of these hold for Lipschitz functions because they are absolutely continuous. And the second nice property is that if f is absolutely continuous on, say, a, b, then integral f prime phi, we know that f prime exists, equals negative f phi prime for every, so this is the integration by parts formula, except that there are no boundary values, and that is taken care of by saying that phi is compactly supported. That means this will not make sense if it's already compact. So you are on R1, and then this is true for compactly supported functions. That means the boundary values will be 0. If you take a large enough interval, then phi will be 0 outside it. So, and then say phi is C1, so that the derivative of phi makes sense in the usual sense. Okay, so that means the integration by parts formula also holds. So this will be for every interval a, b inside R. And too many typos here. So this will be compactly supported on a, b, so that the value at a and b are 0, the boundary values, and we're good. And we will see why I'm specifically putting this down here. Okay, so this kind of ends the R1 to R1 story, and we now know that the Lipschitz functions not only have derivatives almost everywhere, that derivative also satisfies and respects the common rules of calculus. Okay, now to treat the case of Rn into Rm, I will put some simple exercises from advanced calculus. I will put a link in the description of this video to a file which is an exposition of the multivariable calculus through exercise of this type. So it's exercise after exercise and after exercise, and by doing them one can appreciate the depth and subtleties of the theory of differentiability of multivariable functions. Anyway, so one of the exercises is that take any f, not even Lipschitz, just going from Rn to Rm, and then we know that f of x can be written as f1 of x until fm of x for m functions f1 to fm. So these are called the component functions. They're defined by this very equality. Then f is a differentiable at some point x0 if and only if each fi is differentiable at x0. So it looks like a simple exercise, and the solution is actually simple, but the consequence is really deep. It says that the question of differentiability of multivariable functions reduces just to the case of multivariable functions into R1. So here in this example of Lipschitz functions, if we had each fi also becomes Lipschitz. So by Rademacher, each fi is differentiable except for a null set. Now you remove m many times in null set, you still have removed only a null set, and on the complement, your original f is also differentiable. So Rademacher for one-dimensional image will give this one due to this exercise. Okay, I won't give a solution, of course, here. So, for the rest of this video, we will focus on maps that go from Rn into R1, Lipschitz, and n is at least 2, because we've done the case of 1. Okay, now comes the next exercise. If any function f, Rn into R, is differentiable at x0, then for every vector v, the directional derivative of f in direction v at x0, which is by definition the limit t goes to 0 of f of x0 plus tv minus f of x0 divided by t, exists and is linear in V. In fact, we exactly know what that linear function will be. If you take special v's, that means v's to be the standard bases, like ijk in 3D, then we, instead of calling them directional derivatives, we call them partial derivatives. And it turns out that, well, if something is linear, you only need to know it on the basis vectors, because then you know it on every other vector. And so if you know the action of this directional derivative in directions of standard vectors, you get partials. So f1, not f1, sorry, fx1 evaluated at x0, partial of f partial x2 evaluated at x0, and so on, partial of f dxn evaluated at x0. So that's a vector, and then you dot product it with v. So this dot product is obviously a linear map in v. And this vector here we call the gradient of f at x0. So it's all notation, but it's important to keep track of all the notations. Okay, so this started with an if. If your function is differentiable, then the directional derivatives exist. They are linear in v, and this last part is just a simple consequence of being linear. So the important point is that it exists and is linear. Unfortunately, the reverse is not true. That would make multivariable calculus way much easier. If your partial derivatives exist, that does not imply f is differentiable at x0. Probably you've seen many examples of that one. If directional derivatives, because this is only in n directions, what if all of these exist for every v, exists for every v? That even is not enough to say that f is differentiable at x0. What if we know that derivative f at x0 exists and is linear? Is this enough? Unfortunately not. It does not imply that f is differentiable at x0. For this, I'm going to give a solution. You're free to pause and think about one on your own. My solution will be a simple map from R2 to R1. And I take the parabola or something like that. I remove the origin, actually. So I define f of xy to be 1 if you are on the parabola, if y equals x squared and x is strictly positive, 0 otherwise. So this is a function that is 0 everywhere except for that tiny line. It turns out then the directional derivative of f at 0, 0 in direction v is 0 for every v. If you look along any direction, after a threshold, after a cutoff, you will be only in 0 values. So you're just taking the quotient of 0 by t, and then t goes to 0. Your limit is still 0. This function is not differentiable because it's not even continuous. But the real reason that will help us later is that the limit in the definition of the directional derivative, this goes to 0 slower and slower for different v's. And there isn't a uniform delta such that if t is less than delta, all of them simultaneously are small. That does not happen. So if these limits kind of happened at a common speed for all v's, that would be actually just differentiability. But in this example, obviously, that does not happen. There isn't one common delta such that it works for all directions. Okay, now proof, let's talk about a little bit on the proof of Rademacher for Rn into R1. The proof actually follows this line of 1, 2, 3 backwards. So you, I mean, in that, it's trying to find the reverse of this exercise. That in fact, if you are Lipschitz, existence of directional derivatives together with linearity does in fact imply differentiability. So you start with step 1. You show that if you fix v, then partial derivative in that direction exists for almost every x. Okay, and that's a beautiful application of one-dimensional Rademacher plus Fubini. You have your Rn, and I draw just an open domain for pictorial reasons. So you take one direction v, so your v is always fixed throughout, so that is your v. And then when you restrict your function to this line, so you say fix this x0, and then this line is the set of x plus tv's, t being in R. If you restrict your function to this line, that gives you a Lipschitz function from R1, the copy here, you identify with R1, into R1. And then you use the one-dimensional Rademacher to say that except for a null set, in this case, it will be H1. So the Lebesgue one measure null set. Remove an Hn null set from this line, and everywhere else your function is differentiable. But your function being differentiable here is just saying that derivative with direction derivative in direction v exists. So this exists almost L1 almost everywhere on this line. What you do then is you draw another line. You move it parallel to that one. There is a null set now, a new H1 null set, outside which the directional derivative exists. And then that is true for every other line. Now, every line has a null set of bad points. By Fubini, the whole union of all these bad points along all these lines add up only to an Ln null set. So by Fubini's theorem, that's not an obvious fact, but actually the Fubini's theorem is used in this form more often in geometric measure theory than used to actually calculate integrals. If you want to see it through integrals, you have to write the integral of the characteristic function of, say, this u. You integrate characteristic, and that becomes a double integral. Anyway, if every parallel line picks up only a null set, the whole set is actually a null set. So except for an Ln null set, all these derivatives exist, and that completes the proof of step 1. Step 2 will be that this, again, same v from above, which is in particular fixed, you have kept the same v. Then derivative in direction v, the directional derivative in direction v of f at x is linear, which implied, so this is a generic fact, it's not when you have a linear map, this always happens. We saw this above, so derivative of v f at x will be given by this gradient function, because directional derivatives exist, also this gradient exists, and times v. Okay, so the important part is to show that it is in fact linear, and the proof of this is this one-dimensional integration by parts, which we specifically mentioned that it holds for Lipschitz functions. So again, you look at one line parallel to v. Along that line, you have this integration by parts. And how do you reduce to integration along lines? Fubini's theorem again. So these combine to give this fact up here via some calculus. Okay, how far have we gone? There's actually a warning here. Because we've proven that for one v, these facts hold, we have not proven that for almost every x, d v f at x equal grade. Well, let's give this a name because we will keep referring back to it. That for equality star holds. We have not proven it. What we have proven is that for every v, for almost every x, something holds. We have not proven for every x, something holds for every v. So it's about the order of these quantifiers, logical. Okay, so for one v, this holds almost everywhere. That doesn't mean for every x that holds for every v. The problem is that, okay, so you have one v and you have to remove a null set so that these facts hold almost everywhere. Okay, so v, then remove a null set. A null set, but that depends on v. Now, if you choose a different direction this time, then you have to remove another null set, and that will be that can be a completely different one. A new null set and v prime. So if you wanted to have these facts, step 1 and step 2, especially this fact star, if you wanted to have it for all v, then you have to remove uncountably many null sets, and then you can end up with an empty set. So if you remove all nv for all v, you have star. But you may have been left with an empty set after removing too many null sets. And as Pekka Koskela loves to put it, seems like we are dead. Okay, so what is the savior here? The savior here is, of course, that our function is Lipschitz. So Lipschitz assumption is truly needed here. So how? First, we choose, okay, there are several observations due. Number one, partial of f, directional derivative of f in direction v exists, then it implies directional derivative in any scaling of this also exists and equals to this. That's just by definition. Super easy definition. You just multiply this t in the denominator by lambda, and then you multiply the whole fraction by lambda. So the question, so we shall choose only v's from the unit sphere. Okay, the second observation is that now, after removing countably many null sets where vi, I from 1 to infinity, is a dense sequence in Sn-1. So it's a compact set, the sphere, and you can choose a countable dense collection of directions, and for each one of them you remove that bad null set. We now have this star, so we know that directional derivative vi of f along x equals gradient of f along x vi for almost every x and for all vi. So we almost achieved that optimal case where we wanted that to be true for all v. It's not true for all v, but it's true for a good collection of them. And that good collection is just sufficient thanks to the Lipschitz condition. So the last thing is, okay, so what we know is that by this directional derivatives existent, that means x0 plus tvi minus f of x0 divided by t goes to this directional derivative, which is equal to gradient f at x dot vi, but I put this t vi here. So instead of putting it outside the fraction, I made them, combine them all into one. So we know that this converges to 0 as t goes to 0, and that's for every vi. Again, it's not simultaneous for all vi. So once you fix your vi, this converges to 0 just because the directional derivative exists. And let's give this quantity a name, and that is qx. It depends on x0. It depends on v and also on t. Okay, we know that for one single vi, this goes to 0. It does not happen simultaneously for all vi. But again, Lipschitz assumption is strong enough that this will actually lead to proving that so proving the following. So let's write this for an arbitrary x and v. So v is not among that important collection, and v also is arbitrary. So what is true is that this quantity, don't let t go to 0 yet, and this quantity is bounded by Lipschitz constant of f, depending on that, v minus v prime. So this wiggly thing means there are some constants here, but they only depend on n and the Lipschitz constant of f. So that's the most important contribution of being Lipschitz for f here, that if you wiggle a little bit, if instead of looking at direction v, you look at direction v prime, then this is the worst error that you will incur. From this, Okay, the goal. Let's see. The goal. Once we show that qxvt, so for almost every x in our n, this converges to 0 uniformly in V, we are 99% done. The 1% will be take t to be absolute value of y minus x, and take this v unit vector to be y minus x divided by absolute value of this. If you replace t and v by these, this quotient, this qxvt, is just the definition, the fraction that we use in the definition of differentiability. And once we have shown that this convergence qxvt to 0 happens uniformly in V, that means there is the same speed that works for all vectors on your sphere. We will have shown that that quotient goes to 0 uniformly, which is just saying that the function is differentiable, and this linear map here is the derivative. Okay, so that is why we're almost done once we prove this one. And how do you show that? So to show, let's say double star. So I don't want to be too sketchy here. I could, but let's see how much detail we can afford. So to show this, we must show that given epsilon positive, there exists delta positive such that this quotient xvt is less than epsilon for all v in Sn minus 1, that means the uniform part, and for all t that are less than this delta. Okay. Our x is like some good x that we've frozen. To do so, since individually we have q x vi, the good one, t goes to 0. Okay. For each vi, there exists a delta I such that qxvit is less than epsilon if this t is less than delta. So here I had to say negative delta to delta. So for each vi, there is a threshold delta I. So there's also this observation that there exists some capital N such that for every v in Sn minus 1, there exists some vi not too late, that means among the list v1 to v capital N, such that, so that means in finite time we can find a vi that very well approximates this vi. Okay, so it's kind of an epsilon net. So this v1 to vn is an epsilon net on your sphere. Actually, you can use this net idea to produce your dense subset. But anyway, the point here is that you know an upper bound on how late you can approximate a v, by something from your VI collection within an epsilon error. Now you know what to do. So for every VI we have some threshold, and then you take the smallest of them, the worst case scenario. So let delta be the minimum among delta 1 to delta n. Then, okay, we wanted to estimate qxvt for an arbitrary one. So I replace it with x, and I put my favorite vi here. And then I put t, of course. And the price I pay is the difference of qxvi from qxv. And we saw that this is less than v minus vi. So if vi is chosen so that it estimates this vi, so vi and I is between 1 and capital N, is chosen so that this is less than epsilon, then what I end up with is that qxvt is bounded by this epsilon for this qxvit, because and I choose my, of course, t less than this common delta, which was minimum of delta I between 1 and n. Then, okay, this is less than epsilon because vi is among this list and delta I is bigger than delta. And then for the other one, we had this approximation of v by vi. And that is, of course, less than epsilon. So, given epsilon positive, we did find a delta positive such that absolute value of qxvt is less than epsilon. Of course, if you write out the proof with the constants and things, you can exactly get epsilon without the wiggly less than or equal to sign. And let me one last time recall what this qxt was so that you can see how close we are to the proof of differentiability at x. So differentiability, so this would be qtv minus f of x minus gradient of f at x dot product with v. So we have proven then that for almost every x, the following is true, that for every epsilon positive, there exists delta positive such that this is less than epsilon no matter what v you take. For all v in Sn minus 1, all t with absolute value less than delta. Okay, and by the trick that I had shown you, this is basically just differentiability at x. One thing that I kind of feel bad about is I never said what type of x will this be valid for, and that is easy to fix. So when we pick this dense subset of the unit sphere, okay, here we go. So let me change the color to the blue. So once we pick this vi, there is a bad set, a null set vi for each one of them. So the good set for us, the ultimate good set, where we will show the differentiability of f will be Rn minus union of nvi's I from 1 to infinity. So you remove countably many null sets. That's still a null set that you remove from Rn, and all the rest that happened is true in fact for x in Rn minus this union of nvi. So that's the precise set on which I have differentiability, and that's almost everywhere. So Evans and Gary P, that's the book where I followed the steps of the proof from. So the name of the book is Measure Theory and Find Properties of Functions. This proof can be found in many textbooks because it's such a fundamental result that is needed for all the rest. And the proofs usually follow this path. But the proofs are usually tricky. The notation, for example, and you have to be really thinking about what is proven and what is not. So that's why I decided actually to present this, because I thought I'm adding something. So the intricate parts of the proof is actually to keep track of what you have proved and what you have not. And the rest also is beautiful applications of Fubini's theorem and other geometric constructions. So I hope you enjoyed this video. And now that we know the function is differentiable, we will continue with our work on the area formula. So my next video, video 4, we will prove the area formula now that we have all the ingredients. So until then, have a nice day, and then see you soon.